All right, good morning, everybody. In the last lecture, we were talking about static features in a class, and we had covered static fields. And so now I'm going to go back and talk about static methods. And we've already seen these from the first couple of weeks in the course. So static methods are methods that they're per class members, which means the method belongs to the class, not to an individual object. So you'll also see the term class method for static method. Right? It's just a method that belongs to a class. So when you call the method, you use the name of the class to call the method. Back in our domino class that we were talking about in the previous lecture, we can check whether or not a value is between the minimum and maximum domino values. So you can write a little method called isValueOK. Right? Takes in a value, returns true or false. It can be static in this case because it doesn't need access to the fields of any particular domino object, right? So you don't need to access either side of a domino to tell the user whether or not the number 3 is a valid domino value. Right? The only fields we're using here are the static fields of the class. And so in this case, it makes sense to make this a static method, right? There's no point in having every domino object have its own isValueOK method. When you use a static method, you always use the name, or you should always use the name of the class to call the method. Right? So to use isValueOK, you're going to write domino.isValueOK. Right? And obviously 8, if you input 8 into the method, that should return false. Right? Just like with fields, though, the language allows you to access a static method using the name of an object. Right? So using an object reference. So for example, you could make a domino object and then call isValueOK, right? And that is legal, but considered bad form, right? So you shouldn't do this. The problem if you do this, and someone else comes along and reads your code, they're going to look at the method and say, oh, that's a non-static method that the user is calling, right? Because they made an object to call the method. And only later on will they might realize that that is in fact a static method. Right? So you want to be So you want to call that method using the name of the class instead. Right. This example also makes it clear also makes it pretty obvious why this method can be static. Right. So we made a domino object here, right? But why do we need this domino object to test if the value 8 is okay or not? Right. It doesn't make any sense. Okay, so static fields, static methods. There are no static constructors, so never write static in front of a constructor. That doesn't make any sense. At the beginning of the course, when we were implementing some classes to solve some simple problems, we made classes where everything was static. Right? Some of you might have used non-static fields, which was okay for some of the assignments. But when you make a class where everything is static, that thing is called a utility class. So remember what classes are used for in Java. Their main purpose is to define a type. Right? And so in other words, most classes in Java are used to make objects. Right? Point2 class makes point2 objects. The string class makes string objects. Right? And the way this works, or one way to think about how you make an object is you use the class as a blueprint. Right? So you copy whatever non-static fields and non-static methods your class has, and that produces an object. Every once in a while, so very, very occasionally, right, it's useful to create a class called a utility class that you use to not make objects. Right? So such classes have no constructors because you're not using the class to make objects. And in a utility class, everything is marked as static. Right? It has to be static because you have no objects. So you can't have any non-static features in a utility class. If you look in the standard library, now the standard library is very big, right? Consists of, I don't know how many, but there's probably thousands of classes in the standard library. There aren't very many utility classes. Right? So these are the three, these three are commonly used utility classes, but there aren't very many other utility classes in the standard library. There are some, there aren't very many, right? So math is used to do math, right? So it contains a bunch of mathematical constants and functions, right? Arrays is the class that you can use to perform common operations on arrays. And collections is the class that you can use to perform common operations on lists and sets. Right. So these things are uncommon. The reason they are used, though, is to group together related fields and methods where creating an object is not necessary. Right? So math groups together mathematical constants and mathematical functions. Right? If I want to compute the cosine or the sine of an angle, I don't need a math object to do that. Collections groups together methods that operate on the Java collection, so lists and sets. Right? I don't need to make a collections object to sort a list. Right? So utility classes are never used to make objects. Right? When you use the utility class, only the class itself actually occupies any memory. Right? So when you make an object, every time you make an object, you have to allocate memory for that object. Right? So if there were no utility classes, then every time I needed to compute whenever I needed to compute cosine or sine, I would have to make a math object, which sucks up some memory. That's wasteful. Right? So here, I can compute the cosine and the sine of an angle using just the name of the class. No math object here. Right? If you were to look at the memory diagram for that slide, right, I've got a variable x and a variable y. So there's my variable x and there's my variable y. Right? The math class itself, it's got some static fields in it. Right, pi and e, so pi is the double value that's closest to the mathematical value of pi. E is the double value that's closest to Euler's constant e, little e in mathematics. Right? But when I compute the cosine and sine of a value, right, there's no math object being made. Okay, so how do you make one of these utility classes? Well, it's really easy. Well, it should be very easy for most of you at this point. Right? You just make a class and everything's static. Okay, so a little example is we're going to make a utility class and we're going to calculate Einstein's famous E equals mc squared equation. Right? In this equation, m is the mass in kilograms, c is the speed of light in meters per second, and E is the amount of energy that's equivalent to that amount of mass. Right? Okay, so to make a utility class, you just make a class. So there's my class. Right? I'm going to call it relativity because that's an appropriate name for this particular class. Right? If it has some constants, you just add your constants. Right? If the constants are useful for users of the class, make it public. Right? It's going to be static because this is a utility class. It's a constant, so we mark it final. Right? And when you name a constant, it's typically in all caps. Right? So big C is the speed of light in meters per second, right? Which is roughly, 3 times 10 to the 8 meters per second, roughly. Right? And now you put in whatever methods you think you might need. Again, they're all static methods. Right? So the equation for mc squared, I'm going to call that mass energy. Right? Its input is just the mass. Right? And to calculate it simple, it's just the mass times the speed of light squared. Right? And you return the amount of energy. And that's it. There's your, that's your almost complete utility class. Right? If you want to use the utility class, right? And remember, it's a utility class, so when you call the mass energy method, or if you were to use the value c, you would write the name of the class in front of the method or the constant name. Right? So if you run that little program there, that's 1 gram of mass, right? So a very tiny amount of mass. And you run it through the method, right? You'll end up with that number, with that being output. Right? That's 10 times 10 to the 9, sorry, times 10 to the 13 joules. Right? That's a very big number. Right? So if you can convert a small amount of mass into energy, you end up releasing an enormous amount of energy. Okay, our relativity class does not expose a constructor, right? So go back to the class, right? That's our class as it stands right now. There's no constructor, right? And that's good because we're not supposed to be making relativity objects. It's a utility class. Unfortunately, you can, at this point, write that piece of code and everything will work just fine. So you can, in fact, make a relativity object, which we don't want to let happen. Right? Why does this happen? Well, I told you the reason probably a couple of weeks ago. If you create a class and you don't have any constructors in the class, Java gives one to you. Right? So the compiler automatically makes the no argument constructor. Right? It makes the constructor that has no parameters. Right? And in this particular case, the constructor does nothing because there's no fields. right? So you get the constructor. It looks like it does nothing. In a couple of weeks, you'll learn that it in fact does something. But it looks like it does nothing, right? Even though we didn't put it into the class ourselves, right? And so we're stuck with this small problem that people using our class can in fact make a relativity object. Now, if you try to do this with the math class, this doesn't work, right? So if you were to write math, m equals new math, that doesn't work, right? So we'd like to find a way to stop this from happening, right? And the solution is simple, right? You just create a private constructor yourself in the class. It's private, so anybody outside the class can't use the constructor anyway, right? And as soon as you make at least one constructor in your class, the compiler no longer makes the no argument constructor for you, right? So put in a private constructor. Constructor does nothing. The only purpose of this constructor is to stop people from making relativity objects, right? And so by adding that private constructor, you've now prevented anybody from making an object using your class, right? So the complete utility class always has a private constructor of some kind. It doesn't have to be the no argument constructor, right? You can put whatever constructor in you want, right? As long as you make it private so that nobody else can use it, and as long as you make a constructor, the compiler will not synthesize one for you, right? And so that summarizes the private constructor thing. Okay, and that's a utility class, so dead simple to make, right? It's just a class, everything's static, it's got a private constructor. All right, so in a normal class, so in other words, in a class that's used to make objects, you can put in static fields and you can put in static methods, right? A class where everything is static, pretty uncommon, right? But a class that's not, where everything is not, so a regular class, it's pretty common to actually see static methods. And in particular, you will often see these things called static factory methods. So what is a static factory method? Well, it's called a factory method, right? So the word factory is there because a factory method makes objects, right? So it makes an object and returns a reference to the object back to the caller. Right? The purpose of these factory methods is it lets you make a method that more or less behaves like a constructor, right? So remember what a constructor does, it initializes a newly created object. What does a static factory method do? It creates a new object and returns a reference back to the caller. Right? Now the difference between a factory method and a constructor is your method is allowed to have a name, right? So you get to pick the name. You can't pick the constructor names, right? And the fact that you can't pick the constructor name causes problems occasionally. Okay, so if you've taken calculus, hopefully they've told you what the polar form of a point is, right? If you don't know what the polar form of a point is, don't worry about it, right? If I have this point here, and I know its distance, or if I can compute its distance to the origin, right? So I know its distance, sorry, not if I can compute, if I know its distance to the origin, so I know r, and I know the angle of the, if you draw the line from the origin to the point, and I know the angle between, measured from the x-axis, then you can calculate the coordinates of the point because it's just a point on a circle of radius r, right? So the coordinates of that point is just r times cos theta and r times sine theta, right? So if you are making the point 2 class and you say, hey, I'd like a constructor where if somebody gives me r and theta, I give them back the point r cos theta and r sine theta, right? So you go ahead and write your constructor, right? So the name is point 2, right? You have to pass in a radius and an angle. And for our particular class, it probably makes sense if those are double and double, right? Implementing the constructor is easy, right? You simply calculate r times cos theta and r times sine theta, right? That's your x, that's your y, so I can just call the other constructor with constructor chaining, right? Or I can write this x equals r times r times cos theta, and this y equals r times sine theta, right? But as soon as you put this constructor in, the compiler will flag this as an error, right? You've already got this constructor up here that has a double and a double as its parameters, right? Our new constructor has a double and a double as its parameters. So you have an illegal overload, right? Both constructors have the same signature. If you were to try to call one of these constructors, then the compiler would not know which constructor to use, right? Do you mean this one or do you mean this one? It can't tell, right? So now you're stuck, right? I can't actually include, I have to throw away one of these constructors. So the solution is replace one of your constructors with a static factory method, right? You might see the term named constructor idiom, although you probably won't, to be honest. If you Google that term, you will come across, you'll discover that this is just another term for static factory method, right? So it's called a named constructor because it resembles a constructor, but it has a different name, right? Thus, named constructor. Okay, so how do you do this? Well, you just make a static method, right? So static, right? You give it a name. So I'm going to call this polar because it returns the polar. It returns a point given its polar form. Right? You give it its parameters, right? And now it returns a point2 reference, right? How do you implement it? Well, you calculate the x and y coordinate of the point, right? And then you just make a new point having those x and y coordinates and return the point, right? If you don't like that line there, you can write point2 p equals new point2 xy and then return p, right? Or you can just return new point2 xy, right? Both are fine. And that's it. So that's how you make a static factory method, right? It's just a method. It's just a static method that returns a newly created object. If you're looking at the course notes, and if you're looking at the source code in the course notes, and you poke around in the point2 class, you'll see that it has a companion class called vector2, right? So a point is a point in space, right? And a vector is a two-dimensional vector, right? So it's something that has magnitude and direction. Right? You may have been taught in some of your science and math courses that these are the same thing. They're technically not, right? Point's a point, a vector's a vector, right? And there are a bunch of methods that let you do things with points and vectors. So for example, where here? Okay, so where's point 2? We'll look at point 2. Right, so for example, there's a method called add, right? That lets me add a vector to a point, right? So adding a vector to a point moves the point, right? And it's, what is there to say? Okay, so to move the point by a vector, you just add the x component of the vector to the x coordinate of the point. Right? And you add the y coordinate of the vector. Sorry, you add the y component of the vector to the y coordinate of the point. Right? And that's it. So that particular method there changes the point that you use to call the method. Right? So to call that method, you would write something like p.addv. Right? And that changes p. Right? You'll also find that there's a static method also called add. Right? So there's two versions of add. The second version of add is static, right? So when you call the method, you would write that, right? So the second version of the method, you pass in the point and the vector that you want to add together, right? So there's a point p and a vector v, right? And this does the same thing, but it doesn't change p, right? It returns a new point equal to p plus v. So if you wanted to write something like that mathematically, this is the version of the method you'd call. So this version does not change p, or the point that was used to call the method, and this one does change p, right? So that one changes p, which is like reassigning p back to itself, right? And that one does not change p, right? Makes a new point. Right? Okay, so inside the static method, there's something slightly unusual here, right? So inside the static method, I'm accessing the x coordinate of the point just by writing p.x. Right? So in other words, I'm not using the method x with the round brackets, right? I'm accessing the x field directly. I'm allowed to do that because I'm inside the point2 class, right? So inside the point2 class, you can access the field x or y of any point2 object, right? Not just this point2 object, right? So I'm not restricted to writing this.x. If someone gives me a point object, I can write p.x. Right? Because I'm inside the class, and so the fact that the field is private doesn't matter, right? I can see private fields from inside the class itself. The same is not true of the vector v, right? I'm not inside the vector class, so I can't access its x component directly, right? I have to use the method in this case, right? What you can't do inside of a static method, right? So inside of static method, there is no this reference. Oh, no is no. There is no this reference in a static method. Right? Why is there no this? Because you didn't use an object to call the method. Right? When you call this method, you use the name of the class. Right? Yes, I'm passing in a point2 object, but I'm not using p to call the method itself. Right? Inside the method, this is a reference to the object that was used to call the method. Right? No object, therefore no this. So if you try to write something like this.x, like that, right? The compiler immediately flags that as an error, right? You cannot use this in a static context, right? Because there is no object that was used to call the method, right? So you can't write this.x in a static method, but you can write p.x inside the static method as long as someone gives you the point p, right? So that's fine. So yes, you can access the non-static fields of an object as long as you're given that object from inside of a static method. Wrong. What is this? Oh, this is equals. Okay. Right? And so that explains why there's a matching static factory method for all of these. Right? Two versions of add, one that changes the point and one that doesn't. Right? Two versions of subtract, one that changes the point and one that doesn't, and so on and so on and so on. Right? And so that slide there explains what the difference is between the two. Okay, if you poke around in the in many of the standard library classes, you will encounter static factory methods, right? So the integer class, remember that's the wrapper class for int. It has a bunch of methods called value of, right? So integer dot value of 1 makes the integer object whose value is 1, right? When you do, when you write something like integer I equals 4, it's that method that's being called to convert the 4, the int 4 to an integer object. The arrays class has a factory method that will copy another array, right? So it copies that array, returns a new array that's equal to the original copied, right? And the string class has several static methods. One of them is format. If you've used a format string in Python, or if you happen to have programmed in C and you've used a printf function, this is Java's equivalent. Right, so it lets you specify a formatting string to convert 0 or more objects into their string representation. Oops, sorry. Right, and so that's all there is to say about static stuff inside of a class for the time being. Anybody have any questions about static features in a class? The important thing to remember is that if it's static, it belongs to the class, right? It doesn't belong to an individual object. Okay, 15. So we're on lecture deck number 15. And this lecture is all about what does it mean for two objects to be equal. Okay, so you write a class, right? Whenever you create a class in Java, that ends up extending this class called big O object, right? So big O object. So every object in Java is also a big O object, right? The fact that that's true means allows you to write toString or equals, or what else? ToString equals. I guess those are the two we know so far. Right? It allows you to call toString or equals on any reference, right? In our point2 class and in our counter class and in the stopwatch class, right, we don't have an equals method in those yet, right? So you can still write p equals something with our point2 class, right? Even though we haven't defined equals yet, because we got a version of equals from big O object, right? So if I make a point p, right? It's a new point, and I ask, is P equal to P, right? That will print true, which is good, right? An object should always be equal to itself. If I write something like P2 equals P, and then ask, is P2 equal to P, that also prints true, right? Remember what this line of code here does, right? It doesn't make a new point object. It simply says that P2 is another name for P, right? Or P2 and P are the exact, refer to the same point2 object, right? And so P2 equals P is effectively asking the same thing as P equals P, right? So that makes sense that it's also true. As soon as you make a new point object, though, right? So P3 now refers to a new point object. Even if that point object has the same coordinates as P, those two things will not be equal, right? So if you ask, is P3 equals to P, you now get false, right? So what's going on here? Well, if you sketch out the memory diagram for this particular situation, you'll get the following, right? So P is the object here. P3 is the object here, right? P2 is also the same object as P, right? So P and P2 both refer to that object there, right? Notice their states are equal, right? So the x and y coordinates of the 2 points are equal, but they are distinct objects, right? So that object is different from that object, right? Which means P and P3 are both refer to different objects, right? The version of equals that you get from object tests if two references refer to the same object, right? So x equals y is true if and only if x and y are references to the same object, right? The other way to think about this is you look in the box here, right? And these are the values that are being used to test whether or not these things are equal, right? So is P equal to P? The answer is yes, right? Is P2 equal to P? The answer is yes. Is P3 equals to P? The answer is no, right? 700 is different than 600, right? So equals is literally looking at the value that's stored in memory beside the variable, right? And that's the exact same thing that equals equals does. Do I put that? No, it's not here, right? So that's exactly the same. This is right? So if x and y are two references, then if you use equals equals, you are asking the question, do x and y refer to the same object? Right. Okay, classes like point2 should support what's called logical equality. Sorry, I should back up. This is called, you'll sometimes see this referred to as equality of identity, right? Are they the same object? Many classes should do logical equality instead, right? Do the two objects have the same state, or do they have a similar state, right? So for our point2 class, we probably want to test, for equals, we probably want to test, do the 2 points have equal coordinates, right? We probably don't care if they are the same object, right? What we probably care about is, do they have the same coordinates? If you decide that you want to do something like this, so if you want to support logical equality, then you have to replace the version of equals that you get from object, right? And so that's exactly what we're going to do, right? And now, there's this quote here from Angelica Langer. She's she's a software engineering consultant. This quote was, I guess it was relevant some time ago now. So back when Java came out, and when it started to become popular, so this was sometime in the 90s, the 1990s, it would not be unusual that if you looked inside of a class and you looked at equals, its implementation would be different than if you looked at somebody else's class and looked at their implementation of equals, right? And so back in the early days, right, you would think that overriding equals should be easy, right? It turns out that there was a large amount of disagreement on how you should actually implement equals, right? If you look at the older Java textbooks and you look at how they implement equals, they probably all do it slightly differently. Now, happily, today, there's basically 2 ways to do it. There is a third, much more complicated way to do it that we're not going to look at in this course. oops, sorry. If you go to our website, though, and you poke around looking at this series of web pages, you will eventually find out what the much more complicated way of doing this is. Right. Okay, so what we're going to do today, we're going to look at version number 1 of the equals. Right. So what we do today satisfies this thing called the equals contract. Right. So the equals contract is just what the object version of equals says equals ought to do. Right. So this is the documentation for the object class up here. Right. So the object version of equals says that equals must be all of these things. Right. And if you actually read that, it's a very mathematical description of what equals ought to do. Right. And so if you know what an equivalence relation is, and then equals has to be an equivalence relation. Right. If you don't know what it is, don't worry about it. I'm going to tell you more or less what that means. Okay, so what do we require for equals? We require 4 things. Right. An object is always equal to itself, which makes sense. Right. Requirement number 2. If you write p dot equals null, that's always false. It never throws an exception. Right. For the current lecture, we're going to say that only objects that have the exact same type can be equal. Right? So a point can be equal to a point, but a point can't be equal to a vector. Right? Can't be equal to a string either, or something like that. Right? And then finally, if your 2 objects have the exact same type, then they are equal only if their states are also equal. Right? So 2 points are equal if they have the same coordinates. Okay, requirement number 1. X equals X must always be true. Right? Similarly, X equals Y must be true if X and Y are references to the same object. Right? And we know from a few minutes ago, you can test if 2 references are refer to the same object if you use equals equals. Right? So to ensure that requirement 1 is true, you can just put in the little if statement. Right? And it looks exactly like this. Right? So when you implement equals, it always looks like that. Right? It's always public. It always returns a Boolean. Its name is always equals. The parameter is always of type big O object. Right? Now this is slightly confusing. Right? We're inside the point 2 class. This ought to be point 2, would be what many people would argue. Right? The problem is you have to remember we are replacing the version of equals that we got from big O object. Right? So inside big O object, the parameter is type big O object. So this is the version of equals that we have to replace. Right? If you were to mistakenly put in point 2 here, it's no longer replacing the version of equals that you got from object. You are now making a new version of equals, right? Which is the incorrect thing to do. Right? Every standard library method or any other class that calls equals on your object is going to be expecting you to replace this version of equals. Right? It's not expecting you to create your own new version of equals. Right? So it's very important that you write exactly that. Well, you can change the name of object here. You can change that to something else. But it's very important that you always write exactly that first line. Right? If you put in the @override thing here, the compiler will test if you put in the right method header for you. Sorry, the compiler will test if you actually put in the correct method header. Right? Okay, so I want to test are the 2 objects the same, refer to the same object. Right? This also might confuse you. Right? So remember how this works remember how you are going to call equals. Oops, sorry, let me just edit this slide. Oh, sorry. Oh yeah, right. That's what's going on. Okay, so remember that when you're going to call equals, you're going to write something like so point 2 p equals new point 2. Just make it like that. Right? And then we're going to make another point 2, so q equals new. Right? And then we're going to write something like Boolean q p dot equals p dot equals q, like that. right? So remember, that's how you're going to use equals, right? You're going to write something like p dot equals q. Inside the method, right, p and this are the same object, right? So inside the method, this is the name of the object that was used to call equals, so that's p, right? Inside the method, obj is the name of the object that you passed in, so that's q, right? So I would like to test, are p and q the same object? So inside the method, I write this equals obj, right? This is p and obj is q, right? So are they the same objects, right? So that's why you write it that way. Right? Oh, if they're the same object, you return true, and that's it, you're done, right? You don't have to test anything else. Okay, step number 2. An instance is never equal to null, right? So x equals null is always false, and it never throws an exception, right? So I guess we should probably test if this is true, right? You can test for equality to null, again, using equals equals, right? So if the object coming in is null, right? So if obj is null, you can return false, and you're done, right? An object is never equal to null. You can flip the order of these two if statements if you want to, but this if statement must show up at least at this point. If it's not here, then the next thing we're about to do will throw an exception, right? So you have to do this before you do the next thing, right? So step 3, instances of the exact same type can be equal, right? So a point can be equal to a point. So the problem here is that we now have to get the type of an object. We don't know how to do that yet. Inside the object class, there's a method called getClass, right? GetClass returns a class object. Now this stuff here is just going to look like gobbledygook to most of you, right? So just ignore all of this. You won't be able to read that until like week 11 of the course, right? Or week 12 maybe, right? So for now, it just returns a class object, right? So getClass returns an object whose type is big C class, right? And if you look at the short documentation for the method, it says it returns the runtime class of an object. All right, so what that means is that, so for every class that you use in a Java program, right, Java also creates a second class, right? It creates an object of type big C class, right? So for our point2 class, when we use point2 in our program, the compiler, or sorry, not the compiler, the virtual machine ends up creating an object of type big C class that corresponds to the point2 class, right? So for every type of, every class that you use in your program, there is exactly one of these class objects that corresponds to your class, right? So if you use string in your program, there is some big C class object that corresponds to the string class, right? If you use math in your program, there is some big C class object that corresponds to your math class, and so on and so on and so on and so forth, right? The important thing is that for every class in your program, there is exactly one of these objects that's made, right? So if we use point2 in our program, then there's exactly one class object that corresponds to our point2 class, right? And so that's how the virtual machine keeps track of what classes are being used in your program, right? So I can use getClass to determine what is the type of an object, right? I want to test if that thing there, right, has the exact same type as the object that was used to call the method, right? So the object that was used to call the method is called this, right? Its type I can get by calling getClass, right? The argument is called obj. I can get its type by calling getClass, right? And now I can test, are these two things different, right? If they're different, I can return false. That should bother you, right? That not equals, right? So the not equals should bother you. This is a reference type, and this is a reference type, right? They have type big C class, right? That's a reference type, right? I've been telling you every time you use a reference type, if you want to test if they're equal or not equals, you should use the equals method, right? So why am I not writing not round bracket this dot getClass dot equals obj getClass, right? It's because of the fact that is the way that the way the big C class works, right? There's exactly one class object for every class that's used in your program, right? Exactly one object, right? That means getClass always returns a reference to the exact same object for every type in your program, right? So when I write, right? If I write, so for the point2 class, right? If this is point2, and I call getClass on it, right? That gives me back the class object corresponding to point2, right? If obj is also a point2 object, and I write obj.getClass, that also returns the exact same object that method returned, right? So because there's always exactly one object, I can safely use not equals or equals equals here, right? If that's confusing to you, you can come ask me about that again sometime during office hours or after class, I guess, right? But for now, you can simply, I guess, accept the fact that not equals is the correct thing to do here. Okay, what's next? Okay, so what have we done so far? We've got requirement number 1, right? An object is equal to itself, right? We've got requirement number 2, right? An object is never equal to null, right? We've got requirement number 3. Only objects of the exact same type can be equal, right? So if they're not the same type, we return false here immediately, right? Okay, step 4. All right, so step 4 says we would like to now compare the state of the two objects, right? So at this point, right here, right, I know that thing is a point2 object, right? So I would like to get the x and y coordinates of obj, right? Because I want to compare it to the x and y coordinates of this point. Right? The problem is when the parameter has type object, big O object, right? So as far as the compiler is concerned, obj is a big O object, and big O objects don't have x and y coordinates, right? Points have x and y coordinates, big O objects don't. So at this point here, I have to convince the compiler that obj is in fact a point2 object, right? So the way you do that is you use what's called a cast, right? And the syntax for that looks like that, right? So I would like to tell the compiler, hey, obj is really a point2 object. So inside of round brackets, you put the type that you are casting to, right? And then you put all of that in front of the reference that you want to cast, right? Oh, sorry, that should be point2, not simple point2, right? So that right there tells the compiler, hey, I would like you to treat obj as though it were a point2 object. And then I can store that in a variable, right, whose type is also point2, right? Give it another name, so I'm calling it other instead of obj. You can pick another name here, but I always call it other, right? And now you can use other to get the x and y coordinates of the point that was passed in as obj. Right? If you did not have this if statement here, right? So if you just try to cast obj to a point2 object and it's not a point2 object, then in Java this cast fails. So it fails at runtime. When you run your program, you'll get a class cast exception at this point here. Right? And that's why that test is needed here. The test for null is needed here because you're going to call a method using obj, right? If this if statement's missing and obj happens to be null, then null.anything is a null pointer exception in Java, right? So that's why you need that test here. Only once you've written that test can you write the getClass test. Only after you've written the getClass test can you safely do the cast, right? So the order of everything here is important, right? Okay, now we want to test. So at this point here, I finally got the 2 points that I can compare, right? I've got this and I've got other. So now I'd like to compare the x and y coordinates of this and other. Okay, so it turns out there's a recipe for doing this because implementing equals is fairly common. If your fields are primitive, right, but they're not floating point, right? So primitive, not floating point. So basically any integer type or Boolean, right? Just use equals equals to compare the fields. Everything will be fine. Right? If you have a floating point type, you have to convert your fields to a corresponding integer value using one of these two methods. Right? So we're going to be using double to long bits. Right? What the heck does this thing do? Right? So remember, so a double is 64 bits in Java. Right? A long is also 64 bits. Right? So double to long bits takes in a double value here. Right? And so all it does is it reinterprets the bits in your double value as though it were a long value. It doesn't change any of the bits, right? It just looks at the sequence of bits and says, okay, that's a long value, and then uses that long value, right? So that safely converts a double value to an integer value. It doesn't give you the same numeric value, right? It's simply reinterpreting the bits. So that safely converts float to int and double to long, right? But remember, it doesn't give you, that int value is not equal to that float value. That long value is not equal to that double value, right? Because the way that the float and double are represented, their bit patterns are different than the bit patterns for the integers. Right? So I'll explain why you have to do this in just a second. Right? If one of your fields, or if your fields are arrays, you can consider using arrays.equals. And if you have reference type fields, so if your object is made up of other objects, you use equals to compare your fields. All right, so why the heck am I doing this nonsense here? Right? And so the reason is because, well, because one, floating point numbers are weird. And two, you want to be consistent with the way the standard library does things. Right? So the floating point standard says that if you have a value that's not a number, then it's never equal to anything, not even itself. Right? That's just the way that the standard's defined. It's defined that way so that if you try to do something with not a number, all of your operations fail very quickly. Right? So that means double dot not a number equals equals double not a number is always false. And that's probably not what you want. Right? If you're testing, do two objects have the same state? Right? And their state happens to contain not a number, then you probably want to know, do both objects contain not a number? Right? So you can't use equals equals directly on two double values if not a number is a possibility. Right? So what do you do instead? You convert it to a long value using double to long bits. Right? If you do that and compare the two not a number values, that returns true. Right? Because it looks at the bit pattern of that value and compares it to the bit pattern of that value, right? They have the same bit pattern because they're both not a number, right? And so that will return true. Right? To be consistent with the standard library, you have to deal with the fact that -0 is equal to 0 in floating point, right? So that's true in floating point, which kind of makes sense mathematically, right? Unfortunately for the standard library doesn't treat these two as being equal. Right? So it says that the standard library says that -0 is less than 0. And the reason for that is because if you sort a list of double values, right, you want the negative values to appear before the positive values. Right? And so these can't be numerically equal. Right? So the standard library does not treat these as being exactly equal. Right? It considers -0 to be less than 0. So again, if you use double to long bits, right, and compare these two values, you get false. Right? So -0 is not equal to 0 if you look at their bit patterns. Right? So that's consistency with the standard library. That's to deal with floating point weirdness. Right? So what does it end up looking like? Well, I convert the x coordinate of this point to its integer representation. I convert the x coordinate of the other point to its integer representation. Right? If they're not equal, I can return false, right? The x coordinates are different. And then I do the same thing with the y coordinate, right? Is the y coordinate of this point different from the y coordinate of the other point? If the answer is yes, right, then the 2 points are not equal, so you return false. Finally, if you get to the end of the method, right, what do you know? The two objects are not the same object. OBJ is not null. The two objects have the same type, right? Their coordinates are the same, right? So finally you can return true, right? And that's the complete version of equals for point 2. I guess it's basically 20 after, so we'll stop there, and we'll we'll look at another example of equals in the next lecture.